So our next speaker has flown all the way over from Sweden, and boy, are his arms tired. No, sorry. So Dr. Roberto Gramignoli from Karolinska Institute, and he's going to tell you about some cells that they might transplant into the pigs at some point and see if they work.
Thank you. Thank you for the introduction. First of all, I would like really to thank you all for the invitation and for this fantastic meeting that's really fantastic. The organizer, the technical people are really great. And I'm more than happy to show you the results we got in the last year, the results that you guys also pay for, because I got your support since 2010. So we are working on placenta, but not only placenta, we are people working on liver. So as you can see from my tissue, we working with the cells that carry the disease that your children have, unfortunately, but we work in the transplanting of this cell. The way we transplanted the cell require, in America, but all around the world, that we strictly respond to the GMP requirement. What does it mean, GMP? GMP means good manufacturing practice. I don't want to bother you with all the details, but essentially it's a bunch of rules, it's a facility where the insurance that we can produce the cell in a proper way. They carry safety for all the recipient and so on. So we have to, it's a bunch of people, a group of experts, not only us, that we are carrying and checking all the different steps in the procedure. It's from the beginning, from the cells, when we got the tissue, since we got the cells. So as you can see, we have to work in a really particular facility, build up, quite expensive, unfortunately. And we were able to do it both when we were in Pittsburgh, now in Sweden as well. It's a facility that requires a lot of equipment, particular instruments that guarantee the safety for the patient and for the cells. And of course, we can produce the cell and ship it all around the world. So this is not the facility in Karolinska. I'm sorry about that. I wasn't able to take a picture because usually I'm dressed up like you can see here, so I'm not allowed to carry any camera inside the room. So essentially, that's how we're working. We take out the tissue, we process the tissue, we produce the cell, and we produce in such a sterilized environment to be certain that we don't produce any negative effect in the patient receiving our cells. Which cell we're transplanting? For almost 25 years, we're transplanting liver cell, hepatocytes, the cell that carry the disease for PKU, but we're transplanting normal cell to correct the disease. Of course, we had to face several problems during the last 25 years for the production of this cell. We solved all these problems during the time, and we were able to move forward. The first transplant was done 25 years ago, 1992. I wasn't the one done, I'm not so old. So my boss did, actually my mentor, Dr. Strom, who was working with us in University of Pittsburgh, was the first one who transplanting the patient receiving the hepatocyte, so a liver cell, and correct the disease. After that, several other centers did it worldwide. In Sweden, we are doing as well. We are doing in London. Many centers, unfortunately, they went out of business because it's a kind of really complicated procedure. So it's really delicate how you do it. And many institutes, many hospitals decided not to do it any further. They prefer to send the patient to other group like us. But how we do? You already see this picture, as you see. But I like to stress it because I want to be sure that you understand how we inject the cell. The cell, there's no massive surgical procedure. In pediatric as well in adult, we reincannulate umbilical vein, the vein that usually doesn't work after you get burned. We were able to put a catheter inside and deliver the cell straight from your umbilicus through the liver. Injecting this cell, we are able to correct different diseases, not only metabolic liver disease, that's are mostly the one recipient because that's the most successful one, but we are also able to bridge the patient to the organ transplant and to rescue people who has an acute failure for overdose or mouse or mushroom poisoning, for example. That's what happened before. This is probably the most important slide for me because I want to stress the point that when we inject the cell, we do not need to repopulate the whole liver. To correct several diseases, PKU included, we need to correct 5-7% of the liver mass. So we don't have to replace all the cell. Because the cell for your child, the cell for PKU people, are perfectly fine except for one enzyme and one enzyme only. Injecting the cell, providing that enzyme, we can correct the disease, but we do not need to substitute all the cell, just a certain amount of them. And it's been estimated that 5-7% of replacement is enough to correct the disease, to get a normal phenotype. And we can inject really. Hepatocytes can be cryopreserved, not really well, so that's a problem why we have to look for other cells as well. So, as I showed you, we solved several problems. The only problem we were not able to solve till a few years ago was the source of cell, because we do not have enough liver cell to correct all the disease. We cannot do it. So what we've done, using your support, we've done two different strategies. We investigate every kind of cell source we can. Starting from fetal liver, they didn't work, so I don't want to bother you with that. We decided to use metabolic liver disease. What does it mean? Every time a child, a person, receives an organ because he has a genetic disease, non-PKU in this case, because PKU usually are not transplanting. I'm talking about different disease. Every time they receive an organ, we got that organ who has a genetic defect, we isolate the cell, and we investigate those cells. Because those cells, as I said before, are perfectly normal except for one enzyme, a different one, not the one per PKU. So we thought if we inject those cells who has a different disease in the PKU patient, we might correct the PKU patient without introducing a second disease, because we are not going to repopulate the whole liver. And that's what has been done. The idea was so cool that first to do it was a doctor in Belgium, Dr. Sokol, in 2012, and then we did it in Pittsburgh with Dr. Fox. These two PKU patients, have been transplanted with liver cell. And for what I know, they're quite fine. They're quite stable in normal diet, right? But these are liver cells. These are going under immunosuppression. And we don't have enough cells. So we cannot, unfortunately, treat all the patients we want. We would like to, but there are not enough liver we can use. So we started investigating different cells. And the cell that we came to, and we found are really promising, and we started investigating, are this one, the placenta. So I think everybody of you knows what the placenta is. It's essentially the tissue surrounding the baby. It's the tissue that once the baby is get born, you throw it away. It's going straight to the garbage. So as you can imagine, we are planning to this tissue. Every day there are baby getting, so we can get tissue every day with no problem. The only tissue right now we are using is the one going to cesarean section. Why that? Not because they're different, because sterility reason. When you do a C-section, you are in OR. So this is sterile. Cell are sterile, I'm sterile, so nothing can be introduced in the patient with no risk. How many placenta we have? In the United States, 1/3 of the babies are being delivered by C-section. So 1/3 of every baby is born, we can potentially use to get cell to correct several different diseases. What is the placenta? I don't like to show nasty picture, grossy picture for you, but hopefully this is not gross enough. The placenta is essentially this sac. The baby is inside. So it's quite nice organ. It's bloody, so I'm not going to show you bloody picture. But it's like this. This is what I get. And please, for me, it's strictly important you discriminate. I'm not going to use cord tissue or cord blood. You're going to hear about that for other kind of therapy, for leukemia and so on. But these cells are not coming from the cord, from the tube, are coming from the placenta, and to be precise, to the tissue that I'm holding on my hand. You see, the kind of tissue that surrounded the baby. Why that tissue? Because the tissue is being used for several reasons during the last century. In 1910, before the big war, they've been starting using the amnion to treat different diseases, not genetic disease, wound healing, burn. It's been extremely successful. After that, for 1 century, they've been used the old tissue as a bandage for surgery and so on. Has been proved to be quite useful, especially for ophthalmology. But what we are interested in is the cell, not the tissue. Why the cell? Because those cells are quite peculiar. They're coming straight from the embryo. 8 days, after 1 week after fertilization, when the baby starts developing, a part of the cell get separated from the baby and develop the placenta. So it's the first organ we develop, essentially, the placenta. It's the first one. And the cell creating the placenta are the cells that have the same characteristic as what we usually call embryonic stem cell. So they have the potential to form every kind of tissue in our body. That's a potential. What they have that strictly different from embryonic stem cell is they do not form tumor. Embryonic stem cells, they grow forever. These cells, they don't grow forever. And that is strictly important because that's the reason why they never form tumor. They never form in our animal, great, but most important, they never form in human. Several humans have already been transplanted with this cell, no PKU, other reason. None of them have ever any problem, no immunorejection, no form of tumor. I want to show you a little bit how the pictures are. So as you can see on the right, there is a section of the placenta. placenta is composed by a bottom part, the decidua, that is from the mother. Then there is the chorion, the amnion, and on the top of the picture is where the baby is sitting. This cell in the amnion, in particular the pinky one, called amniotic epithelial cell, are the one we want. Not the other one, not because the other one are harmful, what is called amniotic mesenchyma, but mesenchyma are strictly important for other disease, not liver disease. The amniotic epithelial, instead, they can correct amnion disease. How do I isolate the cell? You invite me to show how we do. And we set up the procedure, GMP grade, and it's quite simple, easy. That's why we teach it to everybody, United States included. We essentially remove the amnion. I was working here, not offense intended. We remove the amnion mechanically, we strip it out, and then we digest it. We expose to a solution, that is an enzymatic solution that we designed, and we get at the end a tube with a single cells. Perfectly. What will make our work also easier is this cell can be freeze. We can freeze them down. We can create a bank. That's what we're doing. We create a bank with all the cells. Millions and millions of cells can be useful for several diseases, not only PKU. And everything has been certified as GMP. We are the first lab in the world doing that. Of course, when we inject the cell into human, we need to be certain that these cells are going into the liver. That's what we are done with the hepatocyte. That's what we're doing with the placenta. Because if you're injecting the cell and they're going somewhere else, they're not harmful, they don't create tumor, but they don't correct the defect. So we decide, okay, we have to investigate how we inject the cell. Are we certain that the umbilical vein is the best one? Yes, it is. Because through the umbilical vein or through the spleen, that's another way that's quite similar, especially in the mouse, we got 95% of the cell reach the liver and stay there. The rest is most in the spleen or a little bit in the lung. Important, never be recorded any kind of side effect, no problem. Even the cell will stay in the lung, they don't create any thrombosis, they don't create any problem. In fact, to be clear, they are so useful, they integrate in the lung parenchyma. Then people in Australia who want to correct lung disease now, they learn from us how to do the isolation and they start in transplanted patients who has lung disease. And while they inject it the other way. Normally, okay, the syringe is not supposed to come there. But anyway, they inject through the regular blood system, it's going everywhere, but mostly in the lung. So that's why, for them, it's quite useful. And really few instead are going to the liver. That's why we don't suggest to use this way. We go into umbilical one, that's quite easy. So once again, how we do it? I borrowed this guy because despite all this superpower, he has a huge problem with one molecule that's kryptonite. It's not phenylalanine, it's kryptonite, but it's quite the same. So we use the umbilical. Let's check inside this. So the liver is there. The cell, we go through the umbilicus, and we start to inject the cells. The syringe, and you inject the cell. Simple, the cell go in there easily. They go inside the parenchyma, they go inside the liver, and they stay there. They don't escape, they stay inside the liver. And once they're there, they get mature, and mature is starting expressing the enzyme that we want to. Actually, all the enzyme, including the one we want, because these are normal cells. These cells are quite interesting. Every cell in human body express an ID card that we usually call HLA, human leukocyte antigen. This is strictly important because every cell in the human body has to express this. It's what makes them peculiar. But when you express this, obviously, it's coming the white cell. The immune system is coming checking the cell. Like when I enter in this country, they check my ID card to see if, okay, are you regular? Can you be are you allowed to enter? And once if everything is fine, okay. If it's not, they require more and more people. And this is not good. So usually end up to be, okay, you cannot. In our body, it's going to be rejected, I mean, they kill the cell. This cell from the placenta, they have another HLA. It's called HLA-G. And this is working as a shield. It's essentially, the right ID card is a shield against the white cell coming, checking them, and they leave. And this cell can survive. They can stay there. HLA-G is quite cool because it's also the key molecule in the placenta protecting the fetus from the mother. So that's been studied for a long time. And this cell, the amnion epithelial cell, not only have HLA-G, but they have also other molecules that have been already observed in several other cells, anti-inflammatory, immunomodulatory. That's why we think they're strictly interesting for us. And we find out that this cell expressing this protein, this molecule on the surface to protect themselves, but they also secrete. These are the only cells who secrete this protein, protecting also the cells surrounding them. And we find out, so essentially this graph showing that this cell has it, and we're starting also measuring how much of this molecule our cell can produce, because they might be used also for other disease. And they produce also another HLA called HLA-E, that is quite close to HLA-G, same effect, and quite rare. This might be a little bit boring for you, but this is one of the important slides, because every time we discuss with other group around the world, we want to be certain they can repeat this study, they can repeat the clinical therapy. It's perfectly fine. But we want to be certain that these people are using the right cells, because you need to characterize the cell. You need to be certain to isolate the right cell. That's why we're asking them, okay, your cell needs to express this marker to prove that these are epithelial cells and not some other kind of cell. Then they should not express the other marker, instead proving that they are not other kind of cell. And more important, they should express some marker like this, they're proving they have this kind of multipotency, embryonic-like. And HLA-G, is quite important for us, because if you want to avoid immunosuppression, that's what you should have. So this is what we call Raleys criteria, essentially. If the cells are negative for the first one, for the first marker, are fine, because if they're positive, they're coming from the mother. If they're coming from the mother, they don't have the shield, so they can cause immunorejection. If they have the other marker, are perfectly fine, are working, and we have the best evidence that this cell can become hepatocytes. I want to finish with the data we collect in the last 2 months, and another observation that's quite interesting is ectonucleotidases. Might not tell you, it's a complicated word, I understand you. I have some problems sometimes to pronounce me too. But essentially, there are two kind of surface molecules as well. They're quite important because they're involved in several pathways for immunity and anti-inflammatory. And this has been observed before only in the stromal cell, never before. So we started, I'm originally from Italy, so now that I'm back in Sweden, I'm close to my own country. I started working with a guy that actually was the first one describing this pathway, and and the alternative pathway. There was an extra slide, it's gone. So these cells from placenta are the only cell ever observed before expressing all the ectonucleotidases ever seen before. And what does it mean? That this cell can metabolize what this molecule called ATP. ATP is strictly important in inflammation and immunorejection. So these cells have a huge potential in immunomodulation. That's why we believe that we have in our hands a potential and great tools for regenerative medicine in general. Because these cells are the only cell ever described to be like embryonic stem cells, so pluripotent, without any risk of forming any tumor. They can grow, but not forever. That's important because I want to control the cell when injected. I don't want them to grow forever. I don't want to get advantage. Are the only cell ever proved capable to become a real liver cell, mature to a real phenotype, able to correct different disease. We have measured that in vitro, but also in vivo, thanks to the work that Christian has done with us. So we correct so far 4 different genetic models. PKU is included. We correct an animal model of PKU. We correct an animal model for MSUD. We have evidence correcting another urea cycle defect, OTC, a complement deficiency. Only injecting this cell in animal with a perfect intact immune system who never seen a single drop of immunosuppression. We inject this cell, human cell in the mouse, they're perfectly fine. They're surviving, they correct the disease. So that's why we believe we might be capable to use this cell to correct liver disease without immunosuppression. We are now isolating the cell, starting banking the cell, create a bank, capable to ship the cell all around the world, despite the fact we have approval to treat the first patient only in Sweden right now. And we have the approval to start treating the first 10 liver disease, 10 patients with liver disease. Which one is going to be the first disease? We are still discussing with the whole team, with the pathologist and so on, because there are several genetic liver diseases we have been treated with the patch that have been successful, but we would love to treat with this cell because they might be successful as well. I've done. I just want to thank you, all the people involved in the study. As you might see, there are plenty of people involved for both sides of the ocean. Both me and my mentor, we moved 2 years ago, and you guys were so nice to support in both countries. I appreciate. And I would like to thank Kristen Zworak in the audience over there, because she did all the study, essentially, in the mouse. She's the one injecting all my cell inside the animal. That's strictly important and quite complicated as well. Thank you all for your support, and please shoot any question you have. Thank you.